I'm Lee Elliott with Invenergy. We're the largest privately owned developer. We have over 25 years experience building over 36 gigawatts worth of wind, solar, and storage. In Nebraska, we have 5 projects and we're continuing to develop. One thing I would like to say is I appreciate this conference. This conference has been amazing to me. I've really learned a lot through this conference. It also is a little nostalgic. I used to work for a telephone company that was in a green building over here, so I'd come over here about once a quarter to visit Lincoln, Nebraska, and I love Lincoln, Nebraska. You've heard Cathey already speak once today. Every time I hear Cathey speak, I learn something. He's just a wealth of knowledge about SPP and the processes. I had worked at SPP for a while and know Cathey well, but every time Cathey speaks, I learn something, and I'm really appreciative of that. So Cathey, I'll let you take it away on your large load.
Thank you, Lee. I like to joke with Lee because I think I see him more now that he doesn't work for SPP. It's really strange. He went to work for Invenergy, and I see him all the time. Maybe that says something about my travel schedule. Okay, so broke this up a little bit according to the agenda, and I will be spending time not just on the large load effort, which is significant, but also on the transmission build-out necessary for all loads and spending some time there. So addressing such as AI data centers and reshoring of manufacturing, which we are seeing. I'm going to walk through some of the load types that we're seeing across the footprint. So first of all, I'm going to talk about ITP. So that's our integrated transmission plan. It's evolved. We've done planning since '06 in SPP in a traditional sense for building out the transmission system. I think now we're at $20 billion of notice to constructs over that time frame, so since 2006. And we're looking at even more transmission investment moving forward, and that is primarily driven by load growth. The ITP has evolved since '06. We've gotten a lot more complex and efficient, but also looking at a lot of different scenarios and sensitivities. And so what our ITP is today. And I mentioned CPP, so I'm not going to really talk about CPP, but CPP is kind of the evolution on top of ITP. So our ITP starts with reliability. We have a mandate with NERC requirements to serve and protect firm service. So that's kind of the baseline. And it's all based, we're not the regional load forecaster. So SPP staff, when things come out and say SPP is building this transmission facility and so forth, well, we didn't come up with these load numbers. These load numbers came from the membership. So they came from the load responsible entities. We do load forecasting in real time, but we do not do long-term. We're actually the only ISO RTO that does not do long-term load forecasting. It comes from our members. So that's kind of the baseline of ITP. The integrated part, the part of the I, is integrating all of the other things. So not just building for reliability. That's kind of traditional planning. It's been around for decades. You forecast your load. You need to make sure you're building infrastructure. Infrastructure that you can't build overnight. So you have to forecast what the usage of the transmission system is going to be in a time frame. The way ITP works is we look at years 2, 5, and 10, and we do it on an annual basis. So we look every year, we look 2, 5, and 10 years out, and we try to optimize. And there's nothing magical about it. It's just we try to predict what it's going to be 5 years from now, what the load's going to be 10 years from now. The members provide that from a reliability perspective. Then what we do is we overlay economic studies. So we look at simulating the market, and that's quite fascinating because we run adjusted production cost software, which is simulating every hour 5 years from now. And so we look, let's say 2030, and we simulate 2030 and the operations of not just the load profiles, but also outages, wind excursions, understanding what the wind profiles are going to look like. Obviously, solar is a lot easier to predict 5 years from now with the sunset and so forth. You can kind of see what that looks like. And then we try to predict what the congestion is going to be on the transmission system based on the usage profile and what we predict for the market. And so that's the economic piece. And then we have public policy needs. The only need we actually had was public policy was the R plan in Nebraska. That did get reclassified as a reliability project. But years ago, it was the only public policy need. But we do have that as part of our overall plan, that if there's certain states or certain utilities that have certain policy needs, we could potentially build out transmission. I suspect as we move to the west, that might actually be used a little bit more with the states in the west, but it's definitely something to just note. And then persistent operational needs. This is more around, like I said earlier, there's a disconnect between planning models and real time. And something that I think most people don't know is the operational model today. I say model, it's the grid right now as we speak. This hour, what is it? It's 10:40. This particular operating hour, I can guarantee you, and I haven't asked ops, I can guarantee you that we have no less than 50 transmission facilities out of service. We've run the numbers, and we've run the numbers over the last few years, and it doesn't matter if it's the heat of the summer in August or if it's the dead of winter, we always have at least 50 transmission facilities out. The reason why I'm calling that out is our planning models are what's called system intact. And so we have an obligation to do N-1. So we trip a line, and you have to protect. Everybody needs their power 24/7. So you have to protect the loss of a single facility. But our planning models are system intact. And every operating hour of the entire year for SPP, we have no less than 50 facilities out. The challenge between the two is we don't know which 50 to simulate because it changes. It's not just in Nebraska, it's across the whole 14-state footprint. And we don't know which 50 are going to be out any given operating hour. I highlight that to say that that's why we have persistent operational issues as a need, because it's not just solving base reliability needs or trying to optimize economics. We also try to figure out what was congested last year. We don't want to build infrastructure for an anomaly, because these are 40-year useful life assets. Some of our transmission facilities are even over 60 years old, and we want a least regret solution. They're also not cheap. They're not cheap. And so whenever we want to design the system and build out transmission, we want to make sure that it's the right transmission. And so that's why we call it persistent. So there's rules around it to say there is a gap between planning and ops. But I'm just highlighting that because it's happening more and more, where things are happening so fast, the load's growing so fast that these things are popping up and congestion's happening. You could probably pull up SPP's LMP contour map, the locational marginal price contour map, and right now on SPP's website, I'm willing to bet that there's price differences on the system and there's congestion. The problem is, and people say, well, why don't you just fix that? Well, we don't necessarily want to fix that because it could just be a situation for today and not necessarily a situation for 40 years. We want to make sure that we're balanced in our investment. So I just say that to kind of set the stage for ITP. The quick version, like I mentioned with CPP, is we take all of that same stuff and we add the generation interconnection to it, and that becomes the CPP and consolidated process. Okay, the 24 ITP was a significant investment for SPP's region. It was over $7.8 billion in upgrades for the region last November. And since then, things have even grown faster in the 25 ITP. Again, this is from our membership itself and what's moving forward. So a couple of things to note. Load growth increased 5% just in that 1 year. Retirements. I think mostly it is because of planning reserve margin, but also the fact that load is growing so fast that retirements have slowed. And this doesn't even show, so the retirements we simulate is 4.8 gigawatts, again, told by our members which resources need to retire. Before our planning reserve margin, I think it was over 14 gigawatts. So a significant amount of planned retirements got deferred. And I don't really want to, I mean, there's certain resources that probably need to retire. I'll just say it that way. They're probably old, they're costly, they're expensive, maybe they're dirty. You know, there's various reasons why utilities want to retire some of these plants. But there's this balance between we have a planning reserve margin, we have an obligation to serve firm load, and we have load growth on top of that. So every external indication is saying you need to keep what you have and maybe even restart things that were just recently retired as well, just to keep the lights on. Nearly the same amount of renewables that we had in our futures from last year in 25. We did introduce spot loads in our future too, and I'll talk to you a little bit about that, but that gives you some analysis. So resiliency conditions, we added this in 24. 24 was more historical look. So we looked at Winter Storm Uri and Winter Storm Elliott in particular. This is similar to the persistent operational issues, and we all know just in our everyday lives, there's going to be extreme conditions moving forward. We're going to have another winter storm. The question is, what does the transmission system and generation system do in that particular winter storm? Because it's probably not going to look like Winter Storm Uri. It's probably not going to look like Winter Storm Elliott. But we have an obligation to protect firm load, and we do have these situations that will happen in our footprint again. And so what can we do about it? We don't want to overinvest or gold plate the system. You don't want to overbuild to sustain a particular storm, but we've worked with our membership to come up with various ways that, again, integrates the need for reliability and economics. And so rather than justify a transmission line solely for a winter storm, you assess the needs of the system for reliability and economics, and then you determine, does this also give us an extra qualitative and maybe quantitative benefit by being able to sustain and keep more power online and not shed load and not cut people's lights off during a terrible extreme event, which is really the worst time to do it. And so that's what we did. So 24 ITP did have some simulations. It was more in arrears. So we tested the system using operational. That was kind of a novel or innovative way of doing it. Resiliency has been tossed around a lot in the industry, and that was the first time to actually do it. For 25 ITP, we worked with our members again, and actually there was a task force, a resiliency task force, that came up with ways to forecast or future cast what we need to look at. And a lot of it had to do with quantifying load shed areas. So you simulate the models, the loads are growing faster, and it's basically like a supply and demand curve. If you're not building enough generation fast enough and you're adding a bunch of load, well, then you're going to spike capacity scarcity pricing, but you're also not going to be able to serve that load. And so we look at that and figure out, okay, are there other opportunities that we can be able to build transmission for resiliency purposes? Okay, let's get into the load stuff. It's a busy slide, so apologies for this, but there's a lot of great information here. So I'm going to pick out a couple things. The 24 ITP, this was a significant transmission investment in this blue. But one thing to note is the number that drove the $7.8 billion is right here. That's the number. This line right here is what drove that portfolio. Now we're talking about the 25 ITP, which is this maroon, and future 2 is inclusive of spot load. So you have the maroon base reliability, which again, we have an obligation to protect firms. So we must solve the reliability needs, which that's significantly more than what drove our largest portfolio last year. So that's the 72 gigs. You add in spot loads and measurement. We can certainly talk about cost control and cost containment and things that we've just been discussing with the stakeholders up to this point for this goal. But what I want to also highlight is just what we're seeing now. So we just locked the models for forecasting our next portfolio. So the way you read these numbers is it's the year in which the portfolio ends. So every ITP is actually a 27-month process, and it overlaps, and it's an annual process we bring. And so when we talk about 25 ITP, we've been working on that process for 2 years, starting with scoping and then modeling, and then the forecast came in last fall, and then we opened it up for FERC Order 1000 process in the spring, and then in this last summer we did the solution development, and now we're doing all the benefits cost ratios and the benefits calculations and introducing that to all the stakeholders and commissioners and the board in the fall. And so we do that every single year. So when you see the 26 numbers, these are the load numbers that we just received from our members that is going to drive the transmission plan for next year. So we're going to develop the needs assessment. We're going to publish that. We usually open up what's called a DPP window for transmission developers to be able to submit solutions to in the March timeframe, and then next year we're going to solidify what transmission solutions are to solve those needs, and then we'll publish the benefits and we'll publish the report next fall. But back to this graph, you see the purple, so that's the base reliability. Again, the BR is base reliability. So this is what the members are telling us that is firm load, and you can see that firm load is higher than the base reliability of the 25 portfolio. So 75 gigs. 75 gigs, we peak at 56. That's what we peak at. So just in that, I'm not talking about these real crazy numbers. I'm just talking about the base reliability number is high. And so when we talked about large spot load, and I mentioned that earlier, that it's not just data centers, and I do have a graph in a minute, it's also the reliability load growth in general across the footprint. And then you talk about the future 1 and future 2, so 110 gig at the max end. Now we weight these. That's another thing. What we do is we build transmission portfolio per future, but then we have a single grid to build for, right? So we can do all these different futures, but ultimately we have to come up with a single plan. And so we do what's called subtraction runs and optimization runs, and it's basically a matrix of solutions that distill down to the most cost-effective transmission portfolio that maximizes the solutions needs, addressing the needs. So we have to maximize the amount of needs we address and come up with a better portfolio. So we're not going to just, take this 110 and just build a transmission plan for it. We have to build that, but then we also have to look at these other two numbers, and we have to build a plan for that, and we have to build a plan for that, and then we come up with an optimal portfolio, and we work with our membership to be able to better do that. So moving on to energy consumption. This is quite fascinating for me, and we're seeing it in operations. We're on track. We pulled the settlement data. We're on track to have energy consumption upwards of 5% this year. And that's through August, maybe September. And so if things hold true for this last quarter of the year, we're on track to be almost 5% energy consumption from 2024. And the reason why it's fascinating to me is traditionally, we've always planned for peak. That's usually what you kind of plan for, is what your peaks conditions are. What we're seeing is a shift in electrification where people are using power constantly. And it's not, again, data centers, it's everything. I think I read an article the other day, and I'm certainly guilty of it with 5 kids. They're like the average household has 26 connected devices. iPads and phones and watches and things like that, coffee pots probably. But it's like it's happening now is the point, right? These are actual numbers. And so what we try to do is be fair to the pandemic, because obviously there was a dip in consumption in the pandemic. So we try to do a reference from 2019 and then try to show what we're illustrating for consumption moving forward. So as you can see, we peaked 2 summers ago, but yet our consumption rate is higher. And so that's kind of counterintuitive, but what we're seeing is traditional shoulder months like April and May and October and November are usually lower months in consumption. Those are being filled in, and so people are just using power all year round. Another point that's not on this slide is going back to this. This is almost double, right? Double this would be 112, so it's almost double our peak number, but our 10-year forecast on the max end is 136% in terawatt hours. It's 619 terawatt hours versus 291. And so from last year's total consumption, we're looking at more than double the usage of the transmission system, which is changing the dynamics of the transmission and generation profile to serve all that load all year long. It's also, I say it's fascinating, it's also a little terrifying because what was traditionally our shoulder months we used for planned and maintenance outages. So we used that kind of lull in the consumption to be able to let things, I mean, they're all machines. So we got to let things be taken down and refreshed depending on, it doesn't matter what technology it is. It's got to have some planned maintenance outages. Well, we're losing that band. We're losing that margin because the consumption is higher during those shoulder months. Okay, so going to load forecast for ERAs. I mentioned ERAs, and this is driven by the the LREs themselves. So this is them saying, hey, we need ERAs, and we need it because we have X number of load that is going to be held accountable from a planning reserve margin perspective. And so the LREs themselves told us that. And that number is 79 gigawatts in the summer of 2030, and it exceeds the future 2 number that our current portfolio that we're presenting to the board's number. So it's just trying to, we keep getting asked, like, what's real? That's the big question. What is real? And do we have enough cost protections necessary that if maybe it's an AI bubble, or maybe we're going to go into a recession, or what happens if some of these customers don't show up? And so I think that's going to be the key discussion moving forward is we have to have this balance between we've got to get started on the plans and infrastructure build for the next layer of highway. We see the need for additional generation. We're already tapped out. The question now is, what's the right size for the highway? Where's the location? And do we have enough cost protections for all of us, basically ratepayers, to not have to pay for and subsidize the need for additional transmission infrastructure for all of the large spot loads? So that's a big part in the conversation we've been having, is how do we do that? Okay. I like this slide too. So this shows the red and blue is really meant to show how fast, so it's not just the magnitude, but it's also how fast the loads are connecting. And so the way you look at this is Nebraska, you see the 26 year 2, that's the Y2, and year 10. So future 1, year 10. So the way you read this is the red bar and the blue bar. The fact that they're so close that's the indicator. It's basically our members saying, it's not this fictitious load that maybe we should start thinking about building in year 20. It's loads that are in year 2 and year 10. So, and it's really across the board. I mean, you can see maybe New Mexico's load kind of is a little bit, it's like half between year 10 and year. But if you can see, most of the states are really high red bars, which really is indicative of how fast the loads are coming. And so what that tells us is that we need to get moving. We need to get moving with the plans so that we can get moving with the infrastructure so that we can connect these loads, be reliable moving forward. Okay, this is a slide I referenced earlier. This is the 25. I think we're working to, well, I know I've seen the graph. I just don't know if it's ready for prime time for the 26 numbers. And so we have a pie chart that we're using for the 26 numbers, which will be different than this. This is the 25 numbers for large spot loads. And so majority of large loads are in the oil and gas industry. I read an article, actually a study that ConocoPhillips did maybe 4 or 5 years ago. And they did this working with the oil industry in the Permian Basin. And it said that electrifying that area was going to be about 6 gigawatts of additional load, which is significant for SPP. I mean, we peak at 56, so you're talking about a significant, like 12% load growth just in Permian Basin. It's about double. I think it's just coincidence, but it's about the same amount of electrification in the Dakotas for the Bakken Basin as well. And so now you're talking about not just 6 gigs, but you're talking about 12 gigs of electrifying those 2 areas. And so in the 25 ITP, you can see that 5 gigs were in the load models for beyond organic load growth. But also you can see that industrial and manufacturing. Now, not all of the the data requests we get all the information for, so that's why there's kind of an unknown. But we do know there's a smelting plant, there's ammonia plants being built, and then there's data centers as well. And I think some crypto is kind of baked into some of the data centers as well. Okay, So what have we been doing since 2007? 2006 was our first plan. This helps show the overall projects that we've issued notice to constructs for in the 2005 for 2023, and then the 24 ITP. So a significant amount of transmission into and out of Nebraska as well. And then you can see some of the, that was the winter storm resiliency and economic project down into Springfield and Branson area. A very large transmission facility for resiliency, but also reliability to increase transfers, north to south transfers, and another one down in the Kansas as well from Nebraska. So, a couple of observations here. These are mostly they kind of look like coral snakes, I guess. And I did not, so I went to LSU. I did not ask them to make this purple and gold. I promise you. But it's our first 765 facility, and that is moving forward as notice to construct, mostly to feed the oil and gas industry down in that area. It was a reliability-based project, but a lot to note is a lot of this red is 345. So I think SPP as a footprint, we're used to 345. That's really our bread and butter from our highway, so to speak, and transmission. And so when we talk about our highway byway process and our cost allocation, 345, really 300 kV and above is the threshold, but 345 is kind of the target voltage for our EHV facilities. What we're seeing is the amount of load growth that SPP is being told by the membership is so significant that it would require 4 to 5 345s to be equivalent to a single 765. The amount of transfers and the amount of load that we're actually seeing necessitates the next build. And so I kind of equate it to the national interstate system and whether or not, are we ready for the investment necessary? Well, the question is, there's no free lunch. There's no option of being free. Deferral is there's a cost there. Reassessing or building lower voltage, there's a cost there. Building higher voltage, there's a cost there. There's really a cost no matter what we do. And so the question is, do we have enough cost protections and cost allocation mechanisms to ensure that everybody's paying their fair freight, but also that we're not exposing the existing rate base to anything that's maybe heavily economic driven, like data centers and so forth. So another observation from an engineering perspective. We looked at 765 back in 2009. We actually had a plan developed in 2009 for 765 kV. The reason why we didn't go for it is two reasons. One, we didn't have this red. So we have to operate in N-1, and when you're carrying 2 gigawatts on a single transmission line, and that's what we're seeing in these 765 plans. So you're carrying over almost 2 nuclear facilities or 4 or 5 large combined cycle plants worth of power on a single transmission line. When you're carrying that amount, you have to be able to sustain its loss. So when you lose that line, because you're going to lose that line. You're going to lose it through tornadoes. You're going to lose it through ice storms. It's going to, there's going to be a problem. You're going to lose the line, hopefully temporarily. When you do, that power goes somewhere. And back in 2009, we did not have this infrastructure to carry that that single loss. And so we didn't have the 345 backbone to be able to carry that loss. And again, back to the highway analogy, it's almost like when the interstate's closed, do you have enough back roads to get to where you're going? And if you don't, then you're not going to get where you're going. That's it, if it's all on just the highway. And so it's very similar here. Now we have the backbone. The second reason we didn't go for 765 15 years ago was that load dropped. Because remember the housing market, everybody remembered the 08 and what happened, but then the oil and gas industry, there was all sorts of impacts between 08 to 2010, a lot of uncertainty, and we saw a load drop, and it dropped. What we were forecasting ended up dropping to 1% or less year over year, and so it was a combination of those two that basically SPP and its members just said, look, let's hold off on the 765 overlay. So Going to 25 ITP, there's a whole lot of red here. When we simulate the models without building the transmission system for SPP, this is simulating load loss. A lot of load loss in Kansas City. You have some in Lincoln. A lot of load loss in Oklahoma. A lot in New Mexico area, up in Basins territory as well. So each of these are just pockets of simulated load loss. And given the magnitude, again, of the load growth that we're seeing, what we've calculated. So anyone know, Colton, what our reliability metric is for loss of load expectation? What's the industry standard? One day in... That's right. I knew he'd know it right off the top. So 1 day in 10. That is the industry standard, right? And I don't even know, I think EPRI did an exercise to figure out where it came from. I don't know, it was in the 50s, and it's maybe in some paper. Someone came up with it as just kind of a metric for balancing affordability and reliability. We could make it better, but everybody would have to pay more. And it's basically a balancing act of how reliable do we want to be. When we simulated this, we had 114 days of load loss in a single year. So rather than 1 day in 10, we had 114 days in 1. So what we're seeing is, and it's not just a magnitude problem of the load growth, it's the fact that we're already stretched as a transmission facility today. And so when you add basically anything to the transmission system today, then you're causing that load loss. And so that's kind of, I don't want to use the word terrifying, but it is a little terrifying just how significant of load loss we're simulating without the transmissions solutions. And again, I didn't really get into the modeling. We use the resource planners data from NPPD, OPPD, MEAN, LES. We use that resource plan, and we still see these load losses. So it's not a matter, because that's the question. People say, well, why don't you build generation closer to load? We did. And you still have to simulate generation loss and a transmission loss. So you still have to simulate it, because that's what happens. The machines fail, transmission fails, and so to protect firm, you have to be able to make sure that you're balancing generation and transmission accordingly. So going to our first phase, I guess, of the overlay is 2025 ITP, 765 in the south. The reason why it's in the south is because that's the load that was given to us by the members in the south for the 25 ITP. That's also come up. Why didn't SPP have a vision for a 765 overlay for the whole footprint? I can tell you that we didn't know that the loads were going to grow Kansas and north until July 30th of this year. And so hindsight's 2020. I would have loved to had a vision for the region, but again, we're not the load forecasters. We rely heavily on our utility members to tell us what the loads are. And if you would have asked us to put together a vision for an overlay July 27th, my team wouldn't have had the data to be able to do that. Now we do. And so this is a question of what can we solve today versus what can we provide for a vision perspective for the 26 ITP to help ensure that the whole region understands what the overall needs are and ultimately benefits and costs as well. But this kind of helps illustrate that. So that's what we did. In fact, my CEO, Laney Nickel, asked me as soon as we came up with the load numbers, which are one of my colleagues calls it the bruise chart. It kind of does look like bruise. It's like a bruise map. And so Omaha got hit in the elbow, and then South Dakota and North Dakota. So this is not indicative of all load growth, by the way. This is just the spot load. So I just want to make sure that's clear. Load's growing everywhere, but this kind of helps illustrate where the spot loads are. So after we received the updated load data in the August timeframe, my CEO said, let's figure something out. What can we do to help illustrate and connect the dots between the southern overlay that we're building out in the 25 ITP versus the full picture of where we're heading? And so obviously this is not a 27-month process. The 27 months has not gone by. We're still working through the 26 ITP, so there's a couple of caveats here, but there's very significant, we've actually rooted this in engineering analysis, what we could do in 2 months. in preparation for discussion with the Regional State Committee and the board. But the point is, with the load growth in Kansas and Nebraska and South Dakota and North Dakota, we see a need for additional transmission facilities that would make some sort of a loop. And we're one thing, my VP of operations, he was like, "You're not going to put 4 lines in a single substation, 4 765 in a single substation." No, the answer is no. That's a terrible visual. We're already talking about, do you have a substation? Basically, you'd have to, from an engineering perspective, you're not going to put 4 lines into a substation like this. That'd be carrying 8 gigawatts of transfer capability into a single point of failure. We're not going to do that. So just be clear. But it is helping illustrate that there's value in connection. That's really the whole point of the transmission system. There's value in a mesh network. Again, these are long-term useful life assets. We look at a 40-year financial assessment. We look at benefits out to 15 years. We use inflation rates and discount rates and calculate net present value. We look at benefits over the long haul. This southern overlay happens to be our most valuable portfolio to date. On the low end, it's 5-to-1, and we've done some aggressive load reductions. So let's say there was some significant AI data bubble and maybe coupled with a recession, and we had a 1% load growth. It's still a 3-to-1 ratio on the low end for the low piece. Now, we have not done the benefits cost ratio for the northern yet. This is purely a engineering exercise from what loads we've been given and what would need to be built for it. And so I don't know if it's going to terminate 2 or 3 more times. And we also have the opportunity for utilities to give us some updated loads, but it helps illustrate kind of what we're thinking. Also, there's power to connect. So MISO has their LRTP, so their tranche 2.1, which is a 765 overlay into Minnesota and Iowa. And we see significant benefits in being able to coordinate and connect for that transfer capability. Yes. 5 minutes? Okay. Okay. Well, I'm going to jump. So the reason why I spent so much time on transmission is it all relates, right? It's a single grid. We need more generation. We need more transmission. And really, it's because of load. It's because of consumption. All of us, all sectors across SPP. Like most good companies, we had corporate goals this year. And one of the corporate goals was it was a reliability goal, specifically for large loads. You had all of these different situations. Dominion had some problems with large data centers tripping offline. Southern California has seen it. We've seen it internationally with all these inverter-based loads. These are significant loads. It's insane how big these loads are. It's like losing all of Wichita in a single, I would say Lincoln, all of Lincoln in a single withdrawal point, at a single location. And so we need to make sure that we're building out the system properly to maintain reliability here. And so we had a corporate goal to be able to establish, let's say, the definition of high impact large load. So we call it HIL. And what additional reliability requirements are necessary to be able to study these inverter-based loads, what ride-through requirements are necessary. So we're party to the NERC Large Load Task Force. We're a part of the ESIG Large Load Task Force. We're party to EPRI Large Load Task Force. But none of those task forces are moving fast enough. They're taking too long to develop the requirements necessary to be reliable. We have a need now. Our customers are wanting to process these load requests today. And so what we did is accelerate that. And we said, okay, we're going to come up with our own voltage ride-through requirements, our own frequency ride-through requirements, our own definition of high-impact large load. So we looked at all the ISOs and RTOs. We looked at what was being contemplated, and we came up with our own over this summer, and that's what we did with HIL. And that's how we defined, 10 megawatts or more qualifies if it's on 69, and 50 megawatts or more is if it's greater than 69. And that is rooted in engineering judgment because of the rated impacts of the lines. It takes up more than a third of a 69 kV facility based on the rating. So it's not just pulled out of the air. It does make sense that it's a significant amount of load that has to go through additional rigor. The other thing I want to talk about is HILGA. So a way that we're encouraging loads, and y'all have probably heard this in the industry, it's been named about 15 different ways. Co-location of loads, energy parks, macro grids, microgrids, behind the meter generation. I probably come up with 15 different names, but they're all sort of similar to the concept of a large load just brings local generation close to the load. And so what we've done is embrace that, and we put a bow around it and said, okay, we're going to do that, and we're going to study it. If you show up and you say, I have a 1 gig data center and I have a 1 gig amount of generation next to that load, then we're going to expedite study. We still have to study the impacts of it on the transmission system. Most of these loads, and I'm specifically now talking about data centers, they don't really want to get in the utility business, but they also have a very high load factor. They require 5 nines of reliability. And so it's not just a matter of building generation local. They ultimately want to be firm, and they want to be treated like a hospital or a neighborhood. They want to be served by transmission, generally speaking. And so what we've done, and I'm kind of running out of time here, but we've come up with, it's really hard to map, but we've come up with basically as many options as possible. Again, what SPP is trying to do is not just accelerate these things, but also we want to get out of the way. And it never fails. Every customer has some unique aspect of what they're trying to do, whether they're trying to back it up with batteries or they're trying to back it up with gas. Maybe they can firm up a little bit because they have excess capacity. Maybe Lincoln has a little bit of excess capacity and they want to, serve this particular large load, but they can't serve all of it. And so what we're trying to do is come up with a way to be this matrices of options so that we can encourage economic development in SPP as a region, but also be reliable. I think that's the real key, is we have to make sure that whatever we come up with is truly reliable. And that's where we landed with HILGA. That is passed by our membership and board. We're actually filing this as well, I think by the end of this week. We've got the draft letter for FERC. And so we're going to ask that. Last 2 things very, very quickly. I didn't come up with these acronyms, but everybody loves them. HIL, CHIL, and PAL. CHIL, so we have the ability to connect generation, and even if the transmission infrastructure is not necessarily built yet, and so it can be a limited operation is what we call it, limited operation interconnection service. We don't have that concept with load. And so the short, I guess, elevator speech there is conditional HIL is some of these loads want to connect tomorrow, and we want to be able to embrace that, but we want, again, similar to the transmission cost allocation concerns, we want to make sure that we're not overly increasing market pricing and exposing all the rest of the footprint. But the whole point of CHIL is to be ultimately firm. So it's a way to bridge the gap between the infrastructure they're bringing and paying for generation and transmission, but it allows them to connect a little sooner. There's a lot more to that to ensure they're moving forward. PAL is different. This is more for low load factor load, like thermal storage. So when we introduced this CHIL and HIL back in July, a lot of, I was actually surprised, there was a lot of use cases that came out and said, we really we want a long-term non-firm product because we really just want to charge from the grid at night only. And so they introduced that use case. Well, we're working through with the membership on what this might look like, and it would just be a highly price-sensitive adaptive load that would not build infrastructure. And so that's the difference between these two. Ultimately, CHIL wants to be a HIL. PAL just wants to be a PAL. So. All right, I think that's probably it.
I hope you've enjoyed Casey. We're going to take a few questions. As I started and said, I always learn so much from Casey every time that he speaks. There was a lot of good nuggets in there today that I hope that everyone picked up on. I was really interested in no matter what time of year, you're always going to have 50 transmission outages.
That's true.
No matter what time of year. So that was the new fact that I learned from you today, and I appreciate you, Casey. Are there any questions for Casey as we move forward? Did you get all yours answered from the last one? Okay. All right. We got one back over here. Here he comes.
You alluded to interregional transmission between Iowa, Minnesota, and Nebraska, I guess. Is that a possibility for cost savings and reliability to do more of that? I'm thinking like, when the sun is setting here, California is still generating more than it needs, maybe. So can you respond to that?
Yes, absolutely. That is part of what we try to assess with the benefits to cost for interregional plans. And in fact, I skipped right over it, but some of the cost savings for this generation right here, these 5 facilities is being funded by the generation interconnection customers, and then the load is the backstop for that. And so there's some cost savings there, which the load would be able to basically benefit from the reliability of the system. Now, the reason why the developers are comfortable with that is similar to the CPP structure, because they understand the upfront cost for affected system in their processing for neighboring concerns. But yes, interregional plans for sure. I didn't have a map for our western expansion, but to your California question, there's even a usage from a time zone perspective. So with the mountain and central time zone and load profile, so it's not just generation and wind and solar, but it's also the load changes that you could see from a transfer perspective. So as we expand to the west and open up the pipes, we can share there as well. All right. I appreciate your time. Thank you.